Hi everyone, Mr. Rowe here. Just tuning in again for another video lesson. This time I decided to look at 2.6, the first measures of spread lesson. I decided to do this one as well just because there's a formula in here that can look a little scary, but really if you break it down, it's not too bad at all. I have most of the note filled out just because it was a lot of tedious work that would have taken a lot of time, but we'll work together to fill in the parts that I left out. So basically we did measures of central tendency, that's measures that focus on the center of the data. Now we're going to focus on standard deviation, which is a measure of spread, which is a measure of how far apart is the data, how spread out is the data. So just a couple key terms. A deviation is a difference between an individual value and the mean. So if you know the average of the value and you take one of your data points and you subtract it, that would be a deviation. So if you have a class average, if your average in my class is 80 and you get a 75 on your test, your deviation would be -5. So the larger the size of the deviations, the greater the spread. So these were and then we get to standard deviation, which is what this lesson's about. By definition, it's the square root of the means of the squares of the deviations. So I know how, that doesn't sound so great. It's hard to really understand what that means, but basically this is going to be a measure of the spread of the data. How spread out is the data? And then you see these two intimidating looking formulas. So if you're doing a population, so if your data set is from an entire population, you would use this one. They're the exact same formula. It's just a different notation. When you're doing the population, you're using sigma, Greek letter sigma, as opposed to if you're using a sample, you just use a small s. When we did population mean, we used the Greek letter mu, but if we did a sample, we used x bar or x hat. And then the only difference is if you're doing a sample, you're actually going to use n-1 in the denominator. So if it's a population, use this version. If it's a sample, use this version. They're pretty similar, and this kind of explains why the n-1 is there. So let's jump to an example. I guess before that, the variance. It's just another measure of spread. It's just the standard. It's just you take your standard deviation and you square it, and you get the variance. So here's the example I want to jump into. So let's pretend that we're gonna play a basketball game with these 14 kids, and I want to split them into two evenly matched teams. So evenly matched in basketball, what we'd want to do is probably get the heights of the teams as similar as possible. We wouldn't want one team to have all the tall players and one team to have all the short players. That wouldn't be very fair. So if you notice here, we've divided the team in terms of heights. Now I've gone ahead and done this already. So I've gone ahead and calculated the average height of the Falcons team. The average height of the Falcons team is 165 centimeters. On the next page, I've already calculated the average height of the Ravens team, and they are also 165 centimeters. So these teams have been split up so they have the same average height. Would you consider this a fair basketball game looking at the raw data? So I'll just give you a second to have a look at the actual values. The average heights on both teams are the same. So the answer is no, because if you notice, you have all the tallest players are actually on this team, but because you also have some of the shortest players, the average works out the same. So this basketball game is not very fair. So this is kind of demonstrating why we need this measure. If I just relied on mean, you'd say, hey, this is a fair game. The average heights of the players are equal, but there's more to the story. So we have more calculations we can do to further investigate the data. So what can we do to calculate a measure of spread? We're going to calculate the standard deviation. So that's that scary looking formula from the last page. So all you need is a table like this. So what this formula is saying to do, if you remember, this big Greek letter here means the sum of. So what it wants you to do is take the sum of each data point x, subtract the mean, and then square it. So you're basically calculating the deviation, then you're squaring it, and then you're adding up all those deviations squared. And then you're taking an average of that. That's why you're dividing it by n. And then you take the square root. So I did most of the work here. I'm gonna put on the finishing touches here with you. I'm just gonna get my calculator. So if you see what I've done here, I've calculated the average. I added up all the heights, which was 1155 centimeters, and divided it by the number of players, which is 7, and I get an average height for this team of 165. So then what I'm going to do to calculate standard deviation is I'm going to take the deviation of each player. How far away is each player's height from the mean? So I take the data point, x, so this first one, Laura, she's 183. I subtract her mean, she is 18 centimeters above the mean. Jamie is exactly at the mean, his deviation is 0. Deepa is 148 centimeters. So if I take that and subtract the mean, I get a negative 17, so that implies that that value is below the mean. So I continue to do this for all the players, and I get all the different deviations. So I've done this part of the formula. I've done all the deviations. Then what I want to do is square them. So I took 18 squared, 324, 0 squared, 0, negative 17 squared, 289. So I take all these deviations and square them. So these should all be positive values if I'm squaring them. So now I've done this part of the formula. I have all the deviations and I square them. And then what it wants me to do is it wants me to add them up. So that's what this part of the formula is. This value right here is all this. It's the sum of the squares of the deviation. All the deviations squared and then added up. So this value is going to go right into here. So on the assessment, you'll be given a table maybe to help you out a little bit. So now I just want to find out what is the average of this value. So I'm going to go 1520, and the number of data points is 7. So you get square root of, I'm just going to get my calculator here. I had my phone, or my real calculator's gone missing, so I'll use my phone here. 1520 divided by 7 is 217.14. Take the square root of that, and you get 14.73, or we'll round it 14.7. That is the standard deviation. There's no units, and as of right now there isn't really much context to this number yet, but I think once we calculate the standard deviation of the ravens, we'll be able to put some context to this value. So that is the standard deviation. Did it want the variance to determine the mean? No. If I wanted the variance, I would just square this value, which would be the 217.14. So next we want to calculate the standard deviation of the ravens. So again, I've gone ahead and done most of the work here, and if you notice, all the ravens, their heights, as you probably observed, are closer to the mean than the falcons. So we'll see how this is going to affect the standard deviation. So I went ahead, calculated the average height, added up all these values. We got 1155 centimeters again. Divided by the 7 players, we got the same average height. But what happens when we go to calculate standard deviation? So I did the exact same thing. I took each height, subtracted the mean, got the deviations. Then I squared these values, so they all became positive and squared. And then I added them up. And then just like the last question, this value goes into here. we finish this calculation, it's going to be the square root of 32 divided by 7. So, final answer coming up, 32 divided by 7. So it's going to be the square root of 4.57. Remove this so we don't have this watermark there. Then I take the square root and I get 2.13. So the standard deviation of this team is 2.13 or 2.1. So now we can compare. So the standard deviation of the Ravens was 2.13 and the standard deviation of the Falcons was 14.7. So what can we conclude about the value of the standard deviation? The conclusion is the larger the standard deviation, the more spread out the data is. It's very obvious by looking at the data points of this Falcons team that their heights are very spread out, especially relative to the Ravens, who all seem pretty close to the average. So the main message here is higher standard deviation equals more spread out data. Lower standard deviation means the data is clustered more around the mean. So it's a measure of consistency. So for example, just say there's like a grad award and you have a student who's got like 98, 97, 78, and 80 and they have a really good average, and just say they have the same average of a person who's got 90, 90, 90, 90. I don't know if those averages work out, but let's say they do. Who would get the award? Well, maybe you would consider, well, who's more consistent? Would you give it to the student who's consistently with the 90s, whose standard deviation would be lower? So there's all sorts of times you'd want to use this calculation. So just to visualize this, and this is kind of a short lesson, I'm going to just plot the data points just so you can kind of visually see the spread out data. So we'll start with the Falcons here. So 183, 165, 148. So 183, this first player is this tall. I already forgot the second player. I knew the third one was 165. You try that. Oh no, second player. Okay. 165, 148, 146. Let's try that again. So 165, 148 is way down here. 146 is way down here. 181, 78, 54. 81 is way up here. 78 is right here. And 54 is around right here. So you can see the average height here of 165. You can see how far away these players are from the mean. So let's compare that to the Ravens, whose heights are 166, 163, 168. So here's 166, 163, 168, 161. So you see how these data points are already clustered around the mean a lot more. 65, 66, 66. So 65, 66, 66. So there you have it. So a way to think about standard deviation, and this is not the definition, it's just kind of an approximation of how you could think of it. It's kind of like the average distance away from the mean each data point is. But that's not what it is. So if you see a low standard deviation, then that means on average those data points are not very far from the mean. So that's it for this lesson. This next page here, using Microsoft Excel, you can work through this if you want. We would go into a computer lab. Obviously, we're not going to be doing that, but if you want to work through that, just get some experience using technology to do that calculation. It's fairly easy. You can do that. So the suggested homework is down here below, and that's about it. And I may post, I think there's one more lesson left in this unit, so I'll probably do a video lesson on that one as well. So expect an assignment probably early to mid next week. So thanks to everyone who participated in that survey. So the general consensus was that the videos were pretty helpful, so I'll continue to do them as long as people find them helpful and are using them. So talk to you later.